Welcome back. Okay, so now we're going to take a look at time series cross validation. So up to now, when we've been assessing forecast accuracy, we've used a simple train test split. So we've held back part of our time series and we've tested our predictions against that in a simulated forecast environment. You must always do that as an absolute minimum, but you can go a bit further if you would like and use what's called cross-validation. So there's two standard approaches. The first is what's called a rolling forecast origin, and that means we're gradually going to introduce more data into our time series, training data, and forecast further into the future. And another option is called the sliding window approach. And that means that we've got a fixed size time series and we're gradually going to slide that along in time and then predict into the future. Now, both of these approaches allow us to get multiple data points about how accurate our time series might be at predicting the future. So it simulates that future forecast multiple times. So because of that, we can look at the distribution of those forecast accuracy scores, and also we can look at the mean performance. So it gives us an idea about how variable our performance of our model might be. And we use this cross-validation to help us select the best model. So you still have a test data set that you've hidden away, but you use your training data in a much more efficient way to try and help you tune and select the best model for forecasting. So let's import pandas and NumPy, as we always need those. So we're going to take a look at the rolling forecast origin to start off with. So I've provided some simple code and examples first about how that works, and then we'll move on to an applied example. So I've set up a function here called rolling forecast origin. So this is a generator. So what this is going to allow us to do is gradually return chunks of the training data as a split, which gives us data to build our model on, and a validation set, which gives us a set that we can test our predictions against. And it's going to do that multiple times, moving that forecast origin further and further into the future. Let's create that generator. And then here is our synthetic data. So we've got a full time series here, which is a really simple time series of some arbitrary values. And we're going to do a train test split on that. So we can see our training sets are these values here, and then we've hidden this away, and we're not actually going to use that. It's just what would we do in practice? We'd hide a test set and we'd have this training set, and we're going to work exclusively with that training set in cross-validation. So I'm going to pass some parameters to that rolling forecast origin generator. So I'm going to pass in the training data. I'm going to pass in a minimum training size, and this means that I won't build any models on data of size less than 4 time periods, and I want to test forecasting 1 period into the future. So if I run that, I'm then going to print out the type of this object, so you can see that it is a generator object, and you know that because I use the yield keyword of object type rolling forecast origin. So you use a generator in a loop. So I'm going to loop through the training and validation sets within my rolling forecast horizon generator, and I'm going to print out the split number. I'm going to print out the training data, and I'm going to print out the validation data so we can see what it looks like. So remember, this is our training data, and then this is how rolling forecast origin splits that training data across several validation splits. So here is our first split. So we've got 2502, 2414, 2800 and 2143. So that is the first 4 data points within my time series, and then I'm predicting this value here, 2708. Then it moves along and it adds an additional point. So it moves that forecast horizon one further point into the future. So you see we take this value and we add that onto the end of the time series to get our new training set, and then we're going to predict one data point into the future. So we've now got 5 in our training set, and we're predicting the next value, which is 1900. Then we take this value and we put that onto the end of our training set, so we've got an even longer training set, and then we're predicting one point into the future, which is 2333. And then finally in our 4th split, we do that again. We add that 2333 onto the end, and then we're predicting the final point in our full training set here, 222. So what we could have done is we could have predicted 2 steps into the future. So let's create that generator again and rerun our code. So we get 1 less train test split. So here's our first split. So again, our minimum training size is 4. And then we're going to predict the next 2 time points into the future, which is these. And then we've got what's called a stride of 1. So we only move this value up onto the top, and then this value moves across, and we bring in the next value in the sequence 233 to predict. And then we move on to the next split. And it's as simple as that. So if you wanted to, you could have a fixed window size. So instead of adding this value on, just adding this value onto there, we could also drop a value from the series, or multiple values from the training test. And if we do that, that's called a sliding window. So that's what I'm doing here. So I've created another generator, which I've called sliding window, and that's just splitting that training data again in a different way. And then what I'm going to do is I'm going to create an instance of that generator, and I'm going to loop through all the training and validation sets within that sliding window generator, and I'm going to print those out. So we set the window size to 4 and the forecast horizon to 1. So just a reminder, here's our full training set. So you can see now across the splits, we've got a window size of 4 each time. That just means our training data is always of size 4. And our forecast horizon is always of size 1. So in our first split, we use our first 4 numbers from the time series, and we predict the 5th. In our second split, we use the second element 4 forward to 2708, and we predict 1900. In the third split, we move along again 1 more. So you can see what we're doing is the start of the training set is moving along each time. So we've got a stride of 1. And that's the only difference between a rolling forecast origin and a sliding window. So the sliding window is gradually moving a window through that training set, whereas the forecast rolling origin is gradually just adding an additional data point to your training set. So let's have a look at that in a full cross-validation example. So I've created a function here called cross-validation score. So that's got a parameter of the model you would like to test. In this case, it's just set up to work with the naive baseline models. We're passing in our training data, we're passing in our cross-validation generator, and we're passing in the metric that we would like to evaluate to use as our score. And I'm going to pass in the mean absolute error. So in here, we've got a list that we're going to store all of our different scores in. So all we're doing is we're looping through the training and test or validation sets within that cross-validation generator. We're fitting the training data to our model, which will be one of our naive baseline models. We're predicting ahead the length of the test set. And then we're scoring that. So we're running whatever our metric function is, where we're comparing our test data to our predictions, and then we're appending that score to a list, and then we're returning that list as a NumPy array. So we're going to bring in seasonal naive and naive 1, and we're going to compare those using cross-validation. And we're also, from sklearn metrics, we're bringing in the mean absolute error. We're going to work as usual with the ED monthly attendances. I'm going to adjust those to the arrival rate. We're going to do a train test split. So because this is what you would do in practice, you would hide some of your data. So that's not part of cross-validation. Cross-validation is about tuning your model and selecting your model. Let's have a look how much data we've got in train. We've got 86 data points. That's quite nice. So the first thing we're going to do is with the naive models, there's no point using rolling forecast origin. We're just going to use a sliding window. More data doesn't make them a better model. We're going to have window size 24 and horizon of 12. So we're going to predict 12 points into the future. And our first set of cross-validation scores, we're going to build using the seasonal naive model. Passing in our training set, our sliding window cross-validator, and the mean absolute error. And then we're going to cast that to a data frame and call describe to get some summary statistics of those scores. So here we go. So it ran 51 splits. That gave us a mean absolute error of 11 with a standard deviation of 2.3. You can see that the maximum was about 17 and the minimum was about 8.5. Okay, so no point just doing cross-validation on its own. We're going to compare models. So we're going to compare the seasonal naive model to the naive one, standard carry the last value forward forecast. So let's run that. All the other settings are the same. You can see here that the mean performance comes out worse. It comes out about 14.5 with a standard deviation of 2.3. And the maximum value is significantly higher. Up here is 16 and here it's coming out as 33. Let's compare those visually. That's often quite useful. So these are comparing the cross-validation scores across each split. In orange is naive 1, in blue is the seasonal naive. So you can see times that there are times when seasonal naive is better than naive 1 is better than seasonal naive, but in general seasonal naive is much more consistent. What we can see, however, is that seasonal naive seems to be having some of its worst performance towards the end of the training set. So that suggests that our performance might be a bit worse in our next sample, in our test set. However, in general, you would expect seasonal naive to be a better forecaster than naive 1. So let's check that out. So we're creating a seasonal naive model here, 12 period one, and we're going to fit all of our training data to that now. We're going to then predict 12 periods ahead, and we're going to have a look at what is the mean absolute error of our test set. So it's come out about 15, which is sort of where we might have expected it to be, given how it looked like the cross-validation was going towards the end. So possibly it loses a bit of power towards the end, but that might come back down again if we went further forward in time. Certainly, naive 1 is very unreliable in terms of accuracy of what forecast it might produce. So that's cross-validation in a nutshell. It's a way to get more information out of your training set about the variability in the performance of your forecasting method. And that's one of the key things you'll be trying to do, is understand how well does your model fit the data, but how well do you expect it to perform out of sample.